Welcome everyone, and thanks for coming to another HPC Hour. Today we have Dr. Vladimir Puzyrev talking today about deep learning in geoscience applications and trends. I read his bio and I am super impressed to see that he's interested in numerical models, numerical methods for partial differential equations, sparse linear solvers, and high performance computing. Given the crowd here at Doug and the people who have attended, it's great. I think this will be a great talk. And we'll all learn something a little bit about how we use AI. Come on in. Use AI in the sort of mineral, well not minerals, but in the earth sciences sector. So please welcome Vlad, and thank you very much.
Yeah, thanks Stuart, thanks for inviting me. It's a pleasure to give this talk and I'm delighted to see so many people. Come in here, please have a seat. So this presentation is about applications and recent trends in deep learning in geosciences. But actually, before we go to geosciences, let me show you a couple of maps. OK, I'm sure that many of you recognize this map. I thought about erasing some of the constellations, but I think you would recognize it in any case because some of you have background in astrophysics and planetary sciences and so on. So this is the most recent evening sky map. If it stops raining, at least for one day, we can see something similar in the sky above. And there is something we can see with our eyes. There is much more we can sense with our physical methods. You can apply AI, machine learning techniques to get information and try to reveal some secrets of the universe if you just look above. And what about the next map, second map? So what do you think about this map? What does it show? Well, I guess people with, I will not tell it myself, but people with geoscience background, you might find actually Australian coastline here and something actually artificial. So it's a map of actually different mineral prospects and geochemical samples taken all around WA. So namely just 1% of one small data set of consisting of surface and drill hole multi-element geochemistry data collected by the Geological Survey here. So we have plenty of data here, maybe slightly less than the entire universe, but still a lot. And maybe the famous German philosopher would, if he lived in Australia, he would probably name among his two favorite things the starry sky above us with all its secrets of universe and so on, and also this Terra, this rich Australian land which also has many interesting secrets here. So this is what I'm going to talk about this in this presentation. Well, if you have a look at Industry 4.0 and if you have a look at the top 20 subtopics fields of Industry 4.0, you will notice even like 3D printing, robotics, obviously self-driving cars and other autonomous vehicles, big data, IoT, sensors, virtual augmented reality. You probably won't find geosciences there. Well, again, but it doesn't mean that geosciences don't use AI. Actually, they're doing quite a lot. And many routine tasks that geoscientists do, they can benefit from using AI, and they will be transformed completely in this fourth industrial revolution, which is about intelligence. So I'm not going to mention all of them. I just mentioned some tiny spectra of them. But basically, modern machine/deep learning use in geosciences now is centered about data processing, interpretation, obviously in modeling, simulation, and in inverse problems, in some prediction of events that you want, unlikely events, assessment of the risk, and so on. Everyone notices this huge increase in publications. We just coin terms machine learning, deep learning, neural networks. It's basically a lot of magnitude increase over the last few years. And another thing which is worth mentioning from technological perspective, actually, most of the geoscience data, for obvious reasons, is spatially connected, regardless whether it's resistivity maps collected with some airborne EM data in Canada, or whether it's vertical seismic profiles coming from 3D seismics collected in northwest shelf of Australia. It's usually spatially connected. So in terms of technology, the most popular type of deep neural networks is convolutional neural networks. Again, it's probably the most popular type everywhere. Very efficient for image processing, video processing, and so on by stacking tens, even hundreds of different convolutional and Boolean layers and some other layer potentially. We can build progressively more abstract representations of the data, and we can solve classification, segmentation, and all other tasks here. So CNNs are used in many applications. Just here I listed a few, starting from things that you can run on your mobile devices or on your PCs, working with images, denoising, impeding, colorizing, whatever, creating videos from images, going to those AI techniques developed by DeepMind, OpenAI, and some other companies, things that NVIDIA develops, Amazon, and all other big companies, including self-driving cars, obviously, virtual augmented reality, surveillance systems, and so on, so on. Yeah. So, and finally, to mention 3 driving factors. So all these things, they were not possible 20, 30 years ago. Actually, the machine/deep learning revolution happened probably around 10 years ago. And there was 3 main driving factors. Obviously, big data that we have now, new algorithms that were developed over the last decades, and computational resources, mainly GPUs. So I put here this slide from NVIDIA, but actually, if you attended Stuart's presentation about computing, many other nice devices are coming in this way. So let's jump into the first field. In the first group of methods, I will list some applications to geophysical and geological domain. There, I'm going to start with a quite routine task of seismic interpretation. So geologists, geophysicists collect huge amounts of data. It has to be processed and analyzed. Conventional seismic interpretations workflows, I mean manual workflows, are very time-consuming and they are subjective. So if you have 3 different interpreters, you probably will get 7 different interpretations of a single data. There was a lot of stuff done in terms of automatic seismic interpretation, and in particular based on deep learning, in particular based on convolutional neural networks, because it's a dominantly used technology in this area. But most of the approaches used in this field, they're based on supervised methods, which in turn requires many manually labeled examples, and it's also a bit time-consuming. So in this example, we try to build at Curtin, we try to build unsupervised automatic seismic interpretation based on a type of network called deep convolutional autoencoder. It's a deep network which consists of encoder and decoder. It has 30 million params in this case, and it allows to automatically classify different pieces of this image. So this is an example of these unsupervised techniques in terms of fascias, seismic fascias interpretation. And on top of it, we added some manual interpretation. So in terms of accuracy, there is still room for improvement because unsupervised methods usually they're not that efficient as supervised. But the nice feature here is we don't need to manually label everything. So after we develop the method, after we find optimal parameters, we can just give large pieces of seismic data to it and get images like that one. So if you want to improve it, it maybe makes sense to blend it with some kind of automatic horizon picking and maybe to less extent to fault picking. But at this stage, it can differentiate between high amplitude, moderate amplitudes, low amplitudes, and give you some approximate image of these fascias here. Another group of methods which we're studying are actually inverse problems and different geophysical problems. So inverse problem is formulated as stated here. We have the measured observations, we have uncertainties associated with them potentially, we have our limitations of our forward modeling, and given all that, we need to find the subsurface model that actually created that data. I'm not mentioning Bayesian inversion, which is actually another topic very interesting, but I'm not mentioning here. Most of the approaches are based on deterministic inversion, where we minimize misfit functional, usually formulated like here. We have data misfit and regularization term. And usually it's done iteratively. So we have continuous model updates. We find search direction using information of gradient, maybe second order derivatives. Gradient can be formulated like here. And this term is actually a forward term. For example, if it's frequency domain electromagnetics, it would be like this one. In seismics, it would be different, and so on, so on. But the common point is that if you're working in 3D, or even if you have some like time-lapse seismic, this would be extremely expensive to compute. And in turns, whole inverse problem becomes computationally very expensive. It might take, depending on different configuration and scale of your data, hours, days, weeks. I heard of an example of student who was making just one inversion during 6 months, which may be a bit extreme, but still it can take many weeks for large-scale data, even if you use large clusters. So instead, people started thinking about developing so-called deep learning inversion or deep learning parameter estimation, whatever. So the idea is the following. We generate the training data, which can be, again, expensive, but it's done only once during offline state. Once the data is generated, it can be real data, but again, you probably need to label it. You train your network using your powerful GPUs, TPUs, whatever. Again, it can take some time, but again, it's just done only once, and you can then improve it. And then the third stage is basically like invoking your neural network. It's usually done less than a second, or maybe within some seconds, and you can estimate your unknown subsurface models from new, previously unseen data instantaneously, which open rooms for real-time inversion, fast parameter estimation, creating conventional starting model, and so on, so on. Yeah, so it has few limitations. Obviously, as a data-driven methods, everything depends on data. So we have this problem of generalization, how a model can adapt to new previously unseen data. Sometimes people mention that actually it is drawn from the same distribution as training data, and it's much easier. But in any case, the model has to be affected across a range of various inputs. So you can split your data in your conventional, non-conventional ways. You can train it for some time. You can determine your stopping criteria, and so on, so on. From inverse perspective, the interesting point is that this method does not require regularization in its traditional sense. So we don't have regularization term just there. Instead, we train it on some training data set, and obviously it would reproduce similar models, similar to what it saw in training. So sharpness, for example, of models, which is quite important for seismic, especially for electromagnetic models, sharpness of models is now determined by the models that we used in training set, and also by the loss functions. You can also tweak this using your neural net loss functions. So one example, it's 2D inverse problem. So it's setup of borehole to surface electromagnetic model when you have anomalous plume somewhere in the subsurface and you want to know its spatial location. So the training set, which consisted of 20,000 of models, was created synthetically using full 3D modeling. So we had 1D or 2D surface receiver setup. We had just one transmitter located in the borehole. And we performed 2D inversion with CNN. So there were 10,000 of unknown resistivity parameters that we tried to approximate using this fully convolutional network. So basically, given this kind of data, 2D surface distribution or 1D data, which is more realistic, we try to reproduce some models shown here. So this is some examples. This was published in Geophysical Journal a couple of years ago. So basically, black lines show the real target locations, and red is shown approximated ones. So this is a binary classification problem on this slide. We can just classify like background or target, and we get quite nice results here. So small amount of targets are misclassified, but their amounts is less than 2%, and average intersection over union is quite high. It also works as actual inversion problem. So now instead of having a binary problem, yes or no, background or target, we have different parameters there. Given the limitations of electromagnetic methods, this is probably the best we can get with this setup. Still, it's 10,000 pixels, where we determined resistivity parameter for each of these pixels. Another good feature of this method, it's highly robust to noise. So we introduce different levels of white noise, and since it's based on convolutional neural networks, so it's image processing techniques, and since we can see visually, techniques that can process images and videos effectively are also highly robust to noise, and only when noise exceeds certain levels we see fast deterioration of accuracy here. Yeah, our method can generalize to different service setups because having this ideal grid of receivers, it's something not very realistic. So if we, let's say, have a more realistically located on our surface setups, we can still, instead of having 4,000 input values, we can reduce it here, and we can still get results which are, so red lines here now show reduced input. As you can see, they're not much different from the full input or from the original. Again, because everything is treated by images and we can interpolate this efficiently. So this is quite expected. Another example of electromagnetic inverse problem, now it's 1D in exploration setup. So previously we had monitoring setup where we had assuming known background without strong resistive or conductive targets and one resistive target. So in this case, we have a 1D exploration scenario where we are looking for resistive targets, which may be hydrocarbons, or for conductive targets in a different method. So we are determining from 100 to 200 independent parameters. And again, as you can see, the different profiles, they match to the original model. So this was synthetic data for 1D frequency domain code. And on next slide, this is real data collected in Denmark. It's this WOC-TM data set. So here we compare on the first row, we compare results of conventional inversion, which was processed by the company who collected this data. This inversion had 5 different layers with not fixed depths of different layers, so nine parameters to invert. Our model had 50 different parameters, so we had fixed layer weights, but much more layers. And as you can see, results are quite similar with small differences here, but using different methodologies, we can get results which are similar to conventional inversion, and this is again executed less than 1 second here. Similar results for seismic inversion, for 1D approximation of seismic inversion. This is synthetic data again, so we generate a large set of training models, 80,000 examples in this case, which represent different seismic velocities, which can correspond, for example, to different formations ranging from coal maybe to anhydrite and so on. And again, we can see the approximate accuracy there. And if we stack different models, we get something like here. Again, everything is executed instantaneously. When we turn to seismic inversion in multiple dimensions, like 2D FWI, in this case, this is a cross-well setup, well 1, well 2. We start having some limitations of our traditional inversion. If we train the models based on these primitives, which can be some anomalies with higher velocity located there, okay, it works well for these models, which come from the same distribution as was originally. It has this performance when models are different. For example, this target has lateral dimensions, while the network didn't see that. So it just produces something which is similar, but obviously doesn't know that some targets may be finite and they may end. So this is an example of having another distribution which is different, very different from training data. So here we conclude that actually more training data is needed, and which is most important, we need higher complexity of models, because we can't really capture realistic features, especially in seismics, which has high resolution. We cannot capture realistic features by training on just some models which have some primitives. So let's a bit step aside from geosciences and go back to machine learning and to some funny stuff. So yeah, maybe some of you can get. So it's Alice. She's working as a columnist for the newspaper. This is some text she wrote about one of our suburbs. Not sure about skyscraper. I haven't seen it when I was coming here, but maybe it was canceled because of coronavirus or whatever. So some art she produced. This is her cats and so on. So I guess those of you who are coming from AI community, you already guessed what is the point here. Okay, so the point is actually almost everything on this slide is fake. It's not real. So it's just I wrote a few words here. Everything else was generated by neural networks, by AI, by robots. So this high-resolution image was made artificially. This person does not exist. It was generated by NVIDIA product style GAN2. So GAN, it stands for Generative Adversarial Network. It's one of the most advanced. It's not the latest, but one of the most latent generative techniques. It can generate many of high-resolution images. Text was also generated by another technique, OpenAI, develops GPT, state-of-the-art natural language processing model. It's, again, not the latest. There are newer models, in this case, which can produce much better text. I just wrote text written in blue, and everything was produced by a neural network. Even this art, it's deep dream generator, and you can imagine even the cat. So I took it from this website. thiscatdoesnotexist.com. You can generate as many pets as you want there. Yeah. And if you are interested more in this AI kind of things, so there was a paper in the Guardian last year when they asked, basically they asked robot to write this article, and this is text. Again, some parts were written by an editor, and then GPT-3 continues this article, and it's actually quite nice quality. So there's a huge progress in these technologies. So this is a famous tweet from Ian Goodfellow, one of the creators of these techniques. Huge progress of generative adversarial models less than in 5 years. It ranged from this low-resolution black and white faces to this style GAN1 by NVIDIA. And this is style GAN2, even better resolution, precision, and style GAN ADA last year added more the diversity and precision on top of that. So when we thought about generation of artificial models to train our codes, this was our main point of focus. So what we did, we used some of these techniques. We extended them to accommodate geophysical model generation. So instead of creating some simple artificial models, we tried to use GANs to mimic different models. So we created a set of stratigraphic models. So for that, we used 3D state-of-the-art modeling code called Badlands. from that, we started with 2D. We extracted different 2D stratigraphic models, and then using physical laws, we created some synthetic density models out of that. And we gave all that to a neural network, and it produced this set of images, which can be used as models for your, let's say, seismic inversion. You can also create velocity, other parameters that you want, or you can generate different stratigraphic layers, which feature some of the realistic stratigraphic geological features here, and you can assign different parameters there, and it would be more realistic than just using some primitives, and this can help in inversion. Code paper is in review now. Code is available on GitHub. If you're interested, just let me know on this. We can also create fake data with GANS. So this is not some kind of marble tiles. This actually extracts from seismic horizontal seismic lines, again in northwestern shelf of Australia. It might be not so easy to guess which one is real, which one is fake. So 15 by 15, something is real, something is fake. I know because it just had some tiny inaccuracies when we cut it. So this one actually is real, another one is fake. But if you don't look at this black artifacts and white artifacts, it's difficult to tell from different tiles which one is real and which will make. And you can generate them based on some criteria, and you can generate them cheap. Many of them can be generated just in 1 second, depending on resolution, and you can enhance your training data set with this synthetic data. Okay, I will briefly mention a few more things to consider in terms of inversion. We need to choose optimal hyperparameters, similar to any other machine learning problems. There is a concept of transfer learning, which we haven't applied previously, but it's quite powerful. Many people apply it for this kind of tasks. Loss functions can be tailored for a particular problem instead of using traditional root mean square error or intersection over units. There's a lot of things to be done in explainability and visualization. I just mentioned them, but keep them aside. Recent studies show that actually, instead of having this traditional parabolic type of shape like underfitting, overfitting, in some cases, people see this double descent curve in terms of accuracy. And this is a zone of zero training risk, zero training error, but actually your validation error also becomes smaller, something to consider. There, some people incorporate physics and math in their problems. It doesn't have to be data-driven at all. If you know many things about physics or math, it makes sense maybe to use one of this approach. So similar approach, I know people use spins, physics-informed neural networks. People are used this kind of things when instead of using traditional linear combinations of basis functions like in finite elements, people use neural networks to combine physics, finite elements, and machine learning somehow. Also, if you have traditional deterministic inversion with some kind of optimization strategies, and you don't want to get rid of it because maybe your problem is too complex, or maybe you don't trust deep learning, you can incorporate some of techniques, for example, like these meta-learning techniques, learning to learn by gradient descent, because basically your optimization problem usually just looks for a search direction, which depends on the gradient, maybe second-order derivatives, and looks for a step, and these parameters can be learned using previous experience and using machine learning. Yeah, so on this, with this we go to the next field, which is geochemistry and some geology here. So different examples where we don't have actually that much of spatial dependencies would be to analyze geochemical databases, samples that I was showing on this second map. So in this example, we analyzed a geological survey of Western Australia WOChem database to identify sample errors, potential anomalies, potential mislabeling, potential unit measurements, and recover missing data. So basically, it's in terms of QA and QC, and also recovering missing data is important because depending on the data set, usually geochemical data sets have between 80 and 90% of unknown data, which can be labeled with some errors. Also, a few percent of potentially erroneous data, again, depending on how clean is this data. This, for example, is quite clean, but there are much more noisy data sets. So, yeah. So the study area, it will probably say something to geologists. It doesn't say much to me. So from numerical perspective, we have very sparse distribution of different elements. For example, gold is measured along the main geological features. Some of the elements like nickel, some base metals here, They are collected around all study regions. Some of them are not collected. So you can start with standard statistical and other techniques such as Kriging, nearest neighbors, but they also have their limitations. So obviously we can start there. We can calculate some correlation between different analytes, between different chemical elements. So obviously if we look at base metals, I need to mention also that not all correlation coefficients work in this case. For example, Pearson, it fails in many cases. So we usually use Spearman rho, like in this case, or Kendall's tau, non-parametric correlation coefficients. So for example, both of them usually produce very, very similar results. For base metals, for example, most of them would correlate with each other. Gold usually doesn't correlate strongly with anything. It's impossible to predict gold from all other things, but there are some correlations, some strong correlations within the set, especially rare earth elements, lanthanides, and others, they correlate quite well here, which actually would explain why the neural network method works. Next step of know your data approach would be to perform PCA. We don't use it in neural networks, but we started with it. It gave some examples. I'm not going into details, but basically this is something that geologists, most of it's quite obvious for geologists, but we came to it independently just by applying statistical techniques such as PCA. It's nice if you want to visualize your data. You can go from multivariate data maybe to bivariate, so you can plot everything in 3D, but still in multi-dimensions we have more complex interactions where PCA has its limitations. So we try to apply neural networks just directly on raw, on process data, but without calculating correlations or PCA, whatever. So we took this training setup. There would be two different sets of results, but basically we use all available data as our training data, and we used different subsets of data which is excluded as a test data. In first case, it would be just randomly taken data from all WA. In second case, we just keep this data as a test data, and we try to see if neural networks trained on this everything, all WA data except this test region, which is something like 90% of all data, if the same geochemical rows can be applied here. The results for the first set, which is taken randomly, base metals, you can see some nice prediction accuracy, especially for nickel. So this is plots estimated versus the actual value. So the closer to the main diagonal, the better. Some of them may be anomalies, some of them may be errors of the method, some of them may be anomalies, potential errors in data. Everything is real data, so you see some noisy results, potential mislabeling, and so on. For these elements, obviously we see the lowest errors. So these plots in the bottom, they show the relative errors. And we see the smallest relative errors in the middle of our range, where we have the largest number of training examples, and at both ends, when we have less samples, obviously accuracy deteriorates. Similar results we can see for some other metals. I'm not showing here rare earth elements, but they were predicted with very huge accuracy. Actually, indium is also quite nice. Gold is the most difficult element to be predicted. Okay, there are some also limitations of measuring gold. You can see these vertical lines. We can determine probably high gold content from low gold content safely, but gold has higher errors in this case, and even larger errors on different data sets, which are noisy. But silver, platinum, and some other noble metals have smaller errors and can be predicted with some nice accuracy here. Another example of predicting nickel, now it's our different setup. So we trained the network on predicting, on estimating nickel content from other known elements from entire WA, but not in this region. And in this region, we assume that we don't know. So these actual nickel values, we assume that we don't know them, but we know everything else, which is just measured there. So we know all this information. It's not 100% there, it's just 10 to 15% because many data is not measured, but still we can estimate nickel content quite reliably. So if you look visually at these pictures, you will see the main geological features, you will see where the main deposits are. Absolute difference errors obviously are large where the magnitude of samples is large, but relative errors are small almost everywhere. We can see 4, maybe 5 samples where over or underestimation, it's more than a factor of 3, but the average error is quite small, so we don't under or overestimate our nickel content here. It was similar for other base metals. For example, it's similar for copper. Copper is a bit interesting because the actual data set has a few very large copper values. Again, we're not 100% sure that they're really that large. Maybe there are some anomalies, but in either case, maybe the method can't capture them because they are so-called rare events in this case, or maybe they're actually overestimated in actual geochem data, but everything else is medium-high copper deposits. Geological picture is determined with similar accuracy. It would not be that simple for gold, because gold is usually the one which has less correlation, so neural networks cannot determine gold reliably from other elements, but many other base metals, precious metals, and many other elements, including rare earth elements, can be determined quite precisely. Similar techniques can be applied to rock type classification, as shown here. So we use the same idea, but now we just try to determine, okay, so there are more than, I think, 200 different rock types in this database, but we just created 10 major rock types: mafic, felsic, ultramafic, regoliths, and so on. And we tried whether it's possible to train a neural network which can predict type of a neural network from its geochemistry. So we don't do any feature engineering. We don't look at silica content or other elements. We just give all raw data, and we're trying to basically we have a standard classification problem with 10 different classes. So this confusion matrix shows, yes, especially where we have lots of elements, such as we have many mafic, we have many ultramafic, and obviously we have many regoliths. Accuracy is quite high when support is low, so we have only 7 elements, for example, of chemical rocks. We see something like that. It's funny because also, for example, the largest mislabels would be in intermediate rocks. So some rocks which are labeled as intermediate rocks, or some rocks which are labeled as undetermined, based on our geochemistry, our method says, look, this one which you call intermediate actually can be a felsic. And this one, which is undetermined, can be felsic or maybe a mafic. So this tool can be used as some kind of suggestion. And also, if you have, let's say, thousands, maybe tens of thousands of different samples from the experts that you trust, you can train this on this information, and you can use it as a tool for younger generation of geologists to kind of some kind of assistance and classification assistance of different rock types from geochemistry. So what are the implications for exploration targeting here? So obviously we can, as I said, from 80 to 90% of data is just empty in geochemical databases. So we tried to, again, we try to look at this study area, and these red circles, they show the high content of gold, potential high content of gold, copper, and nickel in this study area. So with yellow and other dots, you can see known mines and deposits, and this reds is something new, which is not known, which is not developed, but neural network suggests that there might be something there. So as I was saying, for gold, there are potential exploration targets. We don't have high confidence there, but for copper and for nickel, we have higher confidence there, and also from geological perspective, these anomalies appear in some logical places here. So these sites are potential exploration targets, and they're recommended for further analysis there. And finally, something similar for silver. This map shows all known silver content across WA, and this map shows the circles are silver deposits that are known, and that they're predicted also by a neural network classifier, estimator, and the stars show samples which were not analyzed for silver, because actually I think 80% of samples were not analyzed for silver in this database. So these stars, they were not analyzed geochemically, but based on other analytes which are known from these samples, we assume that silver content also would be high in these areas denoted with stars. Still, the most important thing here would be to reach some kind of explainability and get some kind of at least basic uncertainty quantification in this case, because as I said, we need to have confidence. We know that we can predict quite reliably rare earth elements and many metals which correlate with other methods, but we need to assess each of the samples individually. Maybe in some near future we'll be able to build these nice looking models like other people build for different neural networks, convolutional, and maybe we can get some basic uncertainty quantification, which would be a huge step in this direction. Okay, this brings me to conclusions for this talk. So where do we use deep learning? So basically, the short answer would be we should use it everywhere where it's appropriate. So in terms of geoscience, it's everywhere we have this big geo data cleaning, processing, QA/QC. It's very cool, spatially connected data. It's mostly spatially connected, so geochem, geophysical data, not only just images and video, which also appear in the sector. Time series data as well, dynamic physical processes. Some people analyze text even here, obviously control problems, everything which remote control, robotics, autonomous vehicles, and so on. People are using this. I guess the main motivator would be it's evident for everyone that AI is changing society, and current industrial revolution would be done similar to previous ones. I cite this prognosis, which was done just, I think, 12, no, maybe 21 months ago, just before COVID started. They were saying about 800 million of jobs, which can be transformed in 15 years. Even now, maybe this number is larger. There are no reliable prognoses now because everything is a bit undetermined. But now people are more likely to delegate their responsibilities to robots. So changes are coming here, and we need to adapt, and we need to use these new technologies there. So thanks for your attention to all of you. And I would like to especially thank HPC Hour organizers and some of our research collaborators, which helped a lot with this stuff, and some organizations. Thank you.
Any questions for Vlad?
I suppose you seem to be quite confident that AI will really displace jobs. So, I mean, what are you telling graduates coming out who are looking for a nice cushy job and the oil and gas and mining thing? So, drop it, learn maths. What do you say to them?
OK, I excluded a few slides there because I was also showing similar presentations to students. I excluded a few slides, but basically I was asking them to guess how would the job market look in 10 years, because now it's like mining engineer, petroleum engineer, and so on. So maybe in 10 years, I mean, my joke was it would be data scientists everywhere. But obviously, I think similar how we had this involvement of computing literacy in the last decades. Now we can use gadgets, we can use computers, which was not that common maybe 20, 30 years ago. Maybe in 10 years, we will be doing something similar, but now we will have this data literacy.
So I'm an astronomer at CSIRO, and I guess the thing we're kind of thinking about in general in terms of using machine learning is how would you quantify unknowns, right? Which is, I haven't done a lot with machine learning, but in general, like your machine learning is kind of as good as your model. And so is there a way that you've encountered in geoscience or anything else of like categorizing unknowns?
I guess you mean that, OK, one of the most common point of criticism for this is most of these models, they are black box solvers. So we don't know why some decision was taken here. So I know there's a field of explainable AI, which is emerging, and maybe that would be the answer. There's a lot of different attempts to quantify this. But we are also trying to do some uncertainty quantification in our parameter estimation problems, but I guess this still would be the point of near future. There are a few techniques based on Bayesian or non-Bayesian methods for uncertainty quantification in machine learning, but I would say this field is still in its infancy. Even like many people are doing it in the last 5 years, neural networks, geoscience, but from a global perspective, this field is still in its early stages.
There'll still be somewhere for people to work. Working in that unknown area.
So when you generate your machine learning model, how generalizable do you find they are? Or do you see a world where one company ends up with some supermodel that's extremely predictive for their data set, but it's not generalizable to other data sets?
Yeah.
Or have you worked on sort of retraining or adapting a model to new data and things like that?
Yeah. Thanks. Very nice question. Actually, this is a big problem. As I mentioned, generalization to new data, which is not coming from your training data, can be an issue. It usually depends on the problem. For example, with seismic interpretation, because the method is unsupervised, we didn't find much difficulties if we have, let's say, seismic data of similar quality. It can be collected at northwest shelf of Australia, it can be collected close to Victoria coast, it's fine. I'm also actively reviewing some papers on inversion, and I see that, again, it's maybe a bit of limitation of the method. When some people are trying to make 3D inversion with these methods, it's maybe too much simplistic, because you can if you're looking for unknown cubes, like they did maybe 50 years ago in 1D or 2D, just simple geometries, these methods, they would work. But if you want a realistic 3D exploration scenario, maybe it's a bit too early, and we need first to create more general models, maybe using some of these complex model buildings, having millions of different models, and maybe also have a kind of big improvement in how it's done, because now it can generalize, but to some extent.
Could you please explain again what was the goal for using GANS for generation of new data? So you don't have enough data, or what's the goal?
Yeah, so the main idea for GANS was to use, similar to like they use in different fields. So in that case, so for data, this was done more in context of having semi-supervised seismic interpreter. And in this case, this was actually, as you say, to create a large set of still artificial synthetic models, which you can give to your forward modeler so you can get your simulated response, but you can generate many of them artificially, and you don't need to hard code anything. So these models they are much more realistic than your simplistic primitives, and then you can extend your training dataset almost infinitely, and you don't have any issues with using real data. Similar to images, you don't have any issues with IP, and every academic institution or even in industry can use similar techniques to extend their training datasets. So eventually, yes, this is to improve your existing inverse workflows and maybe modeling workflows as well.
But isn't that teaching the neural network what it already knows?
Well, GANs, they would reproduce something which comes from the training dataset. So for example, these faces, they were obviously trained on real people to get this, and improvement in latest versions are actually about variety and diversity of these images, not in resolution, because resolution was already fine. And it would reproduce something similar to what it sees, but this is eventually what we wanted. So we did a lot. Actually, this was a bit laborious task because we had to generate many thousands of models, and we checked many of them because everything which looked a bit suspicious, we removed them and kept those things. So there was a large aspect of data cleaning when preparing this data set.
It just seems strange to me that you learn a bunch of features off these things, then you generate a whole bunch of pictures using the same features, and you're teaching the neural network basically the features that the other neural network learn. So, I mean, isn't it the same information?
But this training data set, it can include maybe as few as several thousands of images. So GANs that generate faces, or I think even those that generate cats, it uses, I think, hundreds of thousands, maybe millions of images. But with the latest style GAN 2, I think with ADA, you can use maybe as less as few thousands of images. But here you can generate as many as you wish. You can generate millions of training samples. So if your algorithm is that complicated and you haven't done that achievement kind of in increasing your generalizability, then the simplest what you can do is just increase your training data set from having a few thousands that you have really to few millions, which you generate artificially. And that is expected to increase your generalizability and overall accuracy.
Isn't it just a combination of the features it's learned, though? Is that?
Well, I mean, it's like, it's similar to people, like it saw many people and generates new people, but all of them have
Brown eyes, and it's made brown eyes, so I guess.
Yeah, there's also an aspect of conditional GANs. So you can use conditional GANs, like now with some neural networks with CGANs, you can generate images and other data which is subject to certain criteria. Here you can also add criteria and generate something that you want. So for example, density models, obviously, because like usually happens, they have increasing density gradient. But different features, they can be present or absent.
But so like that sounds really intriguing to me, but as you just kind of clarified, you had to go through and check it, right? Like I'm thinking of the cat one when it makes something really bizarre. Do you think there's a way to get it so that you wouldn't have to check for those those weird ones that don't make physical sense?
Yeah, I mean, obviously, I mean, if you have, let's say if you have a large data set which is good enough, so if you have training data of maybe at least 1,000, maybe tens of thousands of images of actual people which are good, with the latest techniques, you can use people, you can generate images, for example, people which look like this. There are a few papers with unsuccessful results of different GANs, and you can imagine how they would look like. A bit on nature, there's a lot of things done in image analysis community. But with the current state of the art, if your training data has at least several thousands of samples, maybe a bit more, but at least those, and they are high quality, with these techniques, with this latest style GANs, you can generate something which doesn't have many bizarre models. Yeah. So like here, we choose 8 of them. We don't see many bizarre things there which are not present in training data.
Fantastic. If there aren't any more questions, let's thank Vlad for an interesting talk. It's fascinating to see where AI actually ends up taking us. I saw a fantastic article in China about China where they've got cameras collecting people's faces and people were printing off other people's faces and sticking it on their t-shirt.
Yeah. Actually, another question which I commonly get is, especially from students, is when robots are going to make their AI takeover, which is commonly described. But I always say, look, you have to distinguish between strong AI and weak AI. So strong AI is more this general problem solver and all this cool stuff, and all these things is examples of weak or narrow AI, which is AI developed for one specific target. So these technologies which help you with some of your routine tasks, or which can help in your geophysical, geochemical analysis, they're not going to take over people.